We now move on to section 11.3, which is about integral test and the p-series or p-series test as well. So what does that mean and when do we need those? Well, in 11.2, remember we introduced series, so we learned what a series is, and remember what it is a bunch of sums of numbers, and normally we go from n is equal to 1 to infinity, but we can start with n equal to any number, and n takes on the integer value. So this is something you have to understand. So in 11.2, we discussed what a geometric series is and whether it converges or not, and if it converges we can actually compute its limit. Now this might not happen in every case, but in the case of geometric series and the telescoping series, we can actually compute the sum. Okay. We can compute their limits or their values, you can say. What is a telescoping series? Again, this is something, and when you expand it, bunch of terms in the middle, almost all the terms in the middle cancel, and you are left with only the first and the last term. And then that is what we do when we are finding the partial sum. So these are with adding the limited number of terms, and normally we say n number of terms. And once we have this partial sum as sub n, then we take the limit as n goes to infinity, and we can figure out whether the limit exists or not, and if it exists, that is what the value of the series will be. We also looked at something called a harmonic series. Now this is only one of its kind. So it's something like sigma 1 over n. Well, you can also think of like 2 times sigma 1 over n or sigma 2 over n, so which can be written as 2 times sigma 1 over n. So this is also considered as harmonic series. So these ones always diverge. So this is again something you have to remember, that whenever you see a number divided by n summation, then that is a harmonic series and it always diverges. So we saw the divergence of this by picking up sums and then just noting that every time we add bunch of terms, we are getting numbers which are bigger and bigger, so which we kind of assume or we infer that as we calculate these partial sums, they are becoming larger and larger. So we say that in the case of the harmonic series, that limit of as n goes to infinity of the partial sum is equal to infinity. So we say the series diverges. But actually there are some tests which can be applied, and which kind of formal way of proving that the series diverges. And the first one we are looking at is called the integral test. And the idea is about something we have learned before, using something we have learned, which is improper integral. So we say that suppose f is a continuous function which is positive, which means it's above the x-axis, and it is a decreasing function on 1 to infinity. Okay, so if we have this situation, so what does that mean? It means if you have something, now if this is 1 and so on, 2, 3 and so on. So notice here, before 1 the function could be increasing or decreasing, it could be doing anything, but after the value it gets a value at 1, after that it is a decreasing function, and it is positive, so it has to stay above the x-axis. So if we have this situation, note here, when we integrate, also we are assuming that at these integer values, the values of the function are same as our what you call them, the terms of our sequence. So for example, this will be f of 1, but this is also a sub 1. This will be f of 2, but this is also a sub 2, and so on. So now we are saying that if this improper integral from 1 to infinity f of x dx exists, then the series from 1 to n, 1 n is equal to 1 to infinity, a sub n converges. And if our integral diverges, then the series diverges. Okay, so what is the idea? Remember the summation when we are looking at this integral. So from when you see integral from 0 to 1 of f of x dx, you can assume it's just this area. Then when we find integral from 0 to 2 f of x dx, it is that area plus this area, and so on. So you can see we are keeping on adding areas, but they are becoming smaller and smaller. And eventually we say that the limit exists in this case. So looking at some examples, so if we have to determine whether a series something like this convergent or divergent, we say let f of x equals x squared, then 1 over x squared, sorry, the same thing as what the term is over here. So our an, you can notice, is 1 over n squared. So our f of x will be 1 over x squared. And notice here, this is continuous. So this is continuous. It's positive, and it's decreasing. So it satisfies all the functions. And also, f of n is 1 over n squared. Okay, so in order to check whether this series converges or diverges, we actually find this this integral from 1 to infinity f of x dx. Okay, so which is limit as t goes to infinity of 1 to t 1 over x squared dx, which is the same thing as limit t goes to infinity integral of x to the negative 2 dx, or from 1 to t limit t goes to infinity of x to the minus 1 over minus 1, or minus 1 over x from 1 to t. And now apply the limits. So which is equal to limit t goes to infinity negative 1 over t plus 1 over 1, or just 1. And now notice when I apply this limit, so this limit will become 0. First one will become 0, and the next one is just 1. So we end up getting limit of minus 1 over t as t goes to infinity plus 1. Now this limit is 0, so we end up getting 1 as our answer. So what does that mean? It means since 1 to infinity f of x dx exists, so the summation n is equal to 1 to infinity of n of 1 over n squared converges. And this is happening by integral test. So remember, we must mention the test. Name of the test. Okay, looking at the next example. So if you notice here, think about all the series that we have learned. So geometric series. This doesn't look like a geometric series. You can try putting a number, expanding it, and looking at it. And this is not harmonic. This is not telescoping. So the only thing that we have learned now is we can try finding if it diverges. And so if we use the divergence test, okay, so the divergence test means we are trying to find the limit of n square e to the minus n cube as n goes to infinity. So which is limit as n goes to infinity of n square over e to the n cube. Okay. And you can apply the L'Hopital rule in this case, and you will see that after doing that you end up getting. So what does that mean? It means the test is inconclusive. So remember, when limit comes out to be 0, we do not say that it converges, but we say that the test is inconclusive. So it means divergence test didn't help us. So the next thing we have learned, the test we have learned, is the integral test. Now we will learn a few more tests, but by looking at the series or the nth general term of the series, you have to decide which test you should pick. So what we are going to try now is integral test. So we define f of x equals x squared e to the minus x cubed. And notice here this is continuous. It is, by looking at some of the terms, you will notice it is decreasing, and also that it is positive. So these are the three things we want, and you can draw a graph of it and check that. And so let me show you. The graph looks like, so we have x squared times e to the negative x cubed. Okay, so the graph actually looks like something like this. Okay, so you see after 1, so this is happening at 1, and after 1 it is decreasing. So it satisfies all our conditions, and also f of n will be equal to f of x. So we now look at the integral 1 to infinity and x square e to the minus x cubed dx. So this is going to be limit b goes to infinity. Now you don't have to put t there, you can put any number, any variable, any letter which is different than the letter being used inside here. So 1 to b x squared e to the minus x cubed dx. And how do we do it? Remember, we can do a substitution. So we say let u equals x cube or minus x cube, that will be better. So minus x cube. So the du will be equal to minus 3x squared dx. So the dx equals minus 1 over 3x squared du. So we can substitute in here. So limit b goes to infinity, and you can also do it separately as I have explained before. So this becomes minus 1 over 3 e to the u du equals limit as b goes to infinity. And now we can integrate, so we get minus 1 over 3 e to the u 1 to b, or limit b goes to infinity minus 1 over 3 e to the minus x cube, and limit 1 to b. Plug in the limit, so we get limit as b goes to infinity minus 1 over 3 e to the b cube minus e to the negative 1. So negative b cube and negative 1. E to the minus b cube minus e to the minus 1. So now we can apply this limit, and you can see what will happen, I can put the -3 here in outside and limit as b goes to infinity of e to the minus b cube and minus e to the -1. So this limit goes to 0, so that we end up getting -1 over 3 times -e to the -1, or 1 over 3e. So now we say that this integral x square e to the minus x cube dx exists, which implies summation n is equal to 1 to infinity n square e to the minus n cube converges. So notice here we are able to tell whether the series converges or not converges, or in other words converges or diverges, but we cannot find the limit or find the sum of the series. So again, going back, the geometric series or the telescoping series, these are the two in which we can actually find the limit of the series, but or the sum, but not in every series. Looking at another example here, so again this is ln of n over n. Try to graph the function and you will see that you end up getting, so we are looking at ln of x over x so the function graph looks like something like this. So this is okay, so this is actually not decreasing from 1, because at 1 you will have you will be here, but it's decreasing from n is equal to 2, so this should have been a 2 here. Then it makes sense. Okay, so now what do we do? And also notice here ln of 1 is just 0, and 0 is kind of, you can ignore the term 0. So we again say let f of x equals ln of x over x, and we know that this is decreasing, is positive, and it's continuous. Okay, and we are now going to find the integral from 2 to infinity ln of x over x dx, which is going to be limit as t goes to infinity, or b goes to infinity, whatever you want to call it, not x, because x is being used inside. So b goes to infinity, 2 to b ln of x over x dx. And how do we do that? Well, we can use the u substitution. Ln of u is equal to ln of x, then du is 1 over. And why am I using u substitution? Why not the integration by parts? And the reason is because we know that the derivative of ln of x is 1 over x, which is being multiplied here in the integrand. So that this becomes limit as b goes to infinity of 2 to infinity ln of just u du, okay, which is going to give us u square. So limit as b goes to infinity, and when we integrate we get u square over 2 from 2 to b. Plug in limit b goes to infinity, so ln of u whole square over 2, and you will notice that this is limit b goes to infinity ln of b whole square over 2 minus ln of 2 over 2 whole square over 2. But this quantity is going to go to 0, actually going to go to infinity, so that the whole thing is going to go to infinity. So we say this thing does not exist. So summation n is equal to 2 to infinity ln of n over n diverges. And this is by integral test. So you can say it by, or you can say integral test. Looking at the next example, again this is something kind of intimidating function, and it's not geometric series, not harmonic, not our telescoping. So at this moment the only thing we can think of is integrating, trying to see if we can integrate. So if you think of the function f of x equal to this, the function that is given by here, so we are going to get an integral like this, and you can notice this is something we cannot do. So very hard. So this means it's not a good idea to use the integral test on this series. So we should look for some other tests, and that's what we are going to do, learn new tests in next coming sections.